What are 7 things they don't tell you about the rate equation? And what fundamental concept does even textbooks get wrong? And what mistakes have I seen world-famous professors making? Let's find out. If you've done a high school chemistry course or an introductory university course, you will have been told about the chemical rate equation. It typically looks something like this, and frankly, it's really boring. Now, most courses just teach you how to answer the exam questions, and either forget to explain some essential concepts, or don't have time to explain them properly, or sometimes just get them wrong. So here are 7 things they don't tell you, plus some bonus things at the end that they do tell you, but you have to go looking for them. All right, ready? Let's go. Number 1, it's not about how fast chemicals are produced. Even textbooks get this wrong. This otherwise great textbook twice confuses amounts of stuff with the concentration of stuff. If you think that's the same thing, look at these 2 flasks. One of them is 1 litre and the other is 10 litres. Let's also imagine that we're making a nice blue dye, so we can follow the reaction by the colour change. I love it when we can do that. Now, if both flasks are filled with the same reaction mixture and run at the same temperature, you will see them change colour at the same rate. That's because both concentrations are changing at the same rate measured in molar per minute, or per second, hour, year, whatever's most useful. And let's say the reaction finishes in about 3 seconds. In that time, the 10 litre flask will have made 10 times more blue dye than the 1 metre flask. But this has nothing to do with the chemistry. It's just because one of the flasks is bigger. So most of the time, talking about how fast we produce an amount of stuff is just not useful for us, because we want a calculation that's as flexible as possible and works however much mixture we put in our flask. We want to be able to compare different reactions and predict the importance of concentrations or temperature without having to worry about what kind of container we're using. So the rate equation is all about how fast concentration changes, not about how fast something is produced. Number 2, it's only about increases in concentration. Let's take another look at our model reaction. There are many techniques for measuring changes in concentration, so 2 different laboratories might use 2 different methods for the same reaction. And that might mean that one laboratory will follow the change in concentration of the reactant, and another laboratory will follow the change in concentration of the product. In this simple reaction, both laboratories will agree that the concentration is changing at the same rate. But there's a problem, because one laboratory is talking about a decrease in concentration, while the other laboratory is talking about an increase in concentration. And that means they have to say every time whether they mean decreasing or increasing. And that means there is a high chance of someone making a big mistake. So, all we have to do is agree that we will only talk about increases in concentration. And that means anytime we have a decrease in concentration for reactants or intermediates, we just put a negative sign in front of the number. Number 3, it's all about probabilities. We've already seen one reason why we use concentrations in rate equations, but the most important reason is because the rate equation is actually all about probabilities. When we have higher concentrations of reactants, it means there are more chances every minute for molecules to bump into each other and react. We'll come back to this idea in the next video on understanding reversible reactions and chemical equilibria. So make sure you subscribe if you don't want to miss it. And if you click the like button, it'll help us make more videos. Thanks. Number 4, the rate constant is about how intrinsically easy a reaction is. For elementary first-order reactions, The rate constant tells us how easy it is for the molecule to maybe change its shape or fall apart. For elementary second-order reactions, the rate constant tells us how easy it is for two molecules to react each time they bump into each other. The easier that process is, the higher the rate constant. Number 5. You can't compare rate constants with different dimensions. This is a mistake that I've seen world-famous chemists making. It's easy to think that rate constants are only there to make sure we get the right units for our rate of increase of concentration, i.e. molar per time. But we've just seen that they actually have a deeper meaning about how different things react. A first-order elementary rate constant is fundamentally about how easy it is for a molecule to change shape or fall apart by itself. It doesn't need anything else. And the second-order rate constant is about what happens when two molecules meet. How easy is it for them to get into the right geometry for reaction? How easy is it for them to rearrange their electron clouds when they are in the right geometry? First-order and second-order reactions are fundamentally different, but we don't even have to go down to the molecular picture to understand this. We already know that you can't compare things with different mathematical units. Comparing first and second order rate constants is like saying my table is longer than the speed of your car. It doesn't make sense. And yet, many chemists like to boast about how effective their new catalyst is by comparing the rate constant of their catalyzed reaction with the rate constant of the uncatalyzed reaction. But those processes are fundamentally different, and that means their rate constants have different units, and that means they can't be directly compared. You cannot say my first order rate constant is 1,000 times larger than their second order rate constant. So there. Number 6. Solvents don't just disappear. Now, textbooks don't actually say that the concentrations of solvents disappear. They say they become unity, which means 1. Just the number 1 with no units, which is not the same as 1 molar. And that never made sense to me when I was a student. Pure water is over 50 molar. So how can it make sense to just make this huge number 1? It all comes back to probability. I told you it was important. Let's take water as a common example of a reactive solvent. And let's take the hydrolysis of an acyl chloride as our reaction. Throughout the reaction, until all of the acyl chloride has been completely used up, there are always molecules of water right there. That's what it means if we say that water is the solvent. So the probability of an acyl chloride bumping into a water molecule doesn't change throughout the reaction. And even though the exact concentration of the water will change a tiny bit, it's not going to measurably affect the rate of the reaction. So very simply, the effect of the reactive solvent on the rate of the reaction remains constant throughout the reaction. And that means it actually becomes part of the rate constant. Now, before we get to the final fact, I just want to tell you this video is made at Kyushu University. It's one of the top universities in Japan, and we have science and engineering courses in English, so be sure to check out the link in the description. Moving on, number 7. The rate equation is super important. It's not just a boring exam question. The rate equation is so important because it gives us so much information about how a reaction happens, including the all-important activation energy. And check out this video if you don't know why activation energy is so important. But in addition to that, it tells us exactly why we get what we get from a reaction mixture. Even controlled laboratory experiments usually give us a nasty mixture of unwanted side products that we have to spend time and money separating. And now, just imagine how difficult it is to understand what's going on in a biological cell with its gazillions of different chemicals, all reacting with different things at the same time, but mostly getting it right. Kinetics, and particularly rate equations, give us a way to analyze all these reactions, identify them, and either make them work better or fix them when they go wrong. And that includes everything from finding clean energy sources to designing drugs to cure cancer. And now it's time for the bonus fact. Stuff they do tell you, but you have to go looking for it. Reaction orders don't have to be positive integer numbers. We can have negative reaction orders for things that inhibit a reaction and slow it down. And we can even have fractional reaction orders for products that catalyze their own reaction, like self-copying molecules. They are so much fun. So let me know in the comments if you want a video about them. So, did I miss a secret about the rate equation? Would you like to know more about how we actually know how reactions happen? Or would you like a video about something a bit more complex, like the infamous Michaelis-Menten equation? Let me know in the comments. And if you'd like an animated explanation of kinetics, you can check out this playlist here. Or you can check out this video that YouTube thinks you'll like. And I'll see you next time.